Hi everybody. Today I'd like to talk to you about one last effect of interference, an interference manifestation, a phenomenon called beats. Beats are an audible interference phenomenon that you can hear when you have two sounds of slightly different frequency, not the same frequency, but not too far apart. And what you hear are these things we call beats. Some of you in your notes about interference and resonance and standing waves talked about noise canceling headphones very nicely. I asked you to research that, and many of you said if you've got a noise like a jet engine and you're trying to listen to your music on an aircraft, it's this constant jet engine whine that you're trying to get rid of so you can hear the other sounds that are being played by your headphones. What the noise canceling headphones do, you said, was it listens to the ambient noise and it produces a wave of equal amplitude but opposite orientation. Now, it's kind of strange because sound is not a transverse wave, yet I drew a sinusoidal transverse representation, and I'll talk about that in a second. But if the noise is the black wave, the noise canceling headphones produce a mirror image which creates silence, quiet, cancels out a good majority of the noise you're intending to cancel. I want to remind you that sound is real quick, I want to remind you that sound is not a transverse wave, it's a longitudinal wave. Here's a transparency from our textbook, and there's two forks, and there's a reason for that. I'll get to that in a second. But imagine that one of those forks is not there. As it oscillates, we know it sends out rhythmic compressions, rarefactions, less pressure, high pressure, low pressure, high pressure, low pressure. That these are really the crests and the troughs of a sound wave. It's a pressure wave moving through the air molecules here represented by these little red dots. Remember, these compressions and the rarefactions, the wave itself moves at a speed of about 340 meters per second in air at room temperature. So while this picture is static, nothing's moving, these pulses are in fact moving at a couple hundred, 340 meters per second. Let's look at that second fork. Now, let's say that you have two forks. One of them is slightly different frequency. It looks like the wavelength here, I don't want to get too in the weeds about the formula, but velocity is frequency times wavelength. Here the wavelength appears to be about that big from crest, compression to compression. Here the wavelength appears to be shorter. So if you have a smaller wavelength, you're going to have a higher frequency. If this is a constant of 340, then you know that the smaller the wavelength, the higher the frequency, because these two numbers have to add up to a constant. We could just call it 1, call the speed of sound 1, so we know that, if the frequency is 1, the wavelength is 1. If the frequency goes to 1/2, in order for 1/2 times the frequency, the wavelength goes down to 1/2. In order for the wavelength times the frequency to equal 1, the frequency has to double, right? So frequency and wavelength are inversely proportional for a given wave, sound, light, any wave. So the smaller wavelength is the higher frequency. So the bottom fork is vibrating at a higher frequency. As you can see, there are places where the crests aren't quite lined up, but over here, this crest and that crest are perfectly aligned in space. Here they're a little bit off, and you'll notice here they're totally off. The crest and the trough, so to speak, the rarefaction, those are lined up. What do you think you would hear if you were, now again, these are moving at the speed of sound, but at this instant in time, if you were standing here, would you hear a loud sound or a quiet sound? Crest meets crest. What kind of interference is that? Oh yeah, when they're on top of each other, you get a larger wave. So that's constructive interference, as it says here, and you would hear a louder sound. what would you hear if you were right here at this moment, at this instant, your ear were right there? Well, you'd hear it quiet, right? Because the compression and the rarefaction, the crest and the trough, average out to be essentially zero. When these two add up, you get nothing. So this phenomenon is interesting, and I'd like to talk a little bit more about it in a little bit more mathematical way, and then I'll show you some examples. As I said a moment ago, sound is actually this pressure wave, this longitudinal pressure wave, but we're going to represent it as a sinusoidal wave. So while this is not what a sound wave looks like, you can, in a sense, convert it to a sine function. We have an illustration that does that. Why they use the Greek letter gamma, I don't know. It looks like a Y, I know to you. But anyway, you got it's really frequency 1 and frequency 2. And in fact, I'd like to do, well, we have two different frequencies, frequency 1 and frequency 2. So these are two different waves, and we have just indicated with our pen here the crests of those two different waves. To help you see it, I'm actually going to color these real quick. So the green one, I'm going to highlight in green. And the one that we had indicated in red, I'm going to highlight with red quickly. Okay, so hopefully that's helpful. And let's just talk about this real quick. If these are two different sounds being played in the same room, same time, these pressure waves, which we're representing this as a sine function, but these pressure waves are overlapping. Places they overlap constructively, we get a louder sound, destructively a quieter sound. But because the frequencies are they're not the same frequency, but each one of them is constant, as that wave moves through time and space, we have places where the two waves are clearly on top of each other and doing the same thing, and then we have regions like here where a crest from the red wave and a trough from the green wave meet, and we get a cancellation. Now, what I'd like to do is I'd like to just graph the sum of the green and the red waves down here real quick. And I'm not going to, there is a way to create a one single sine function that is the sum of these two waves, but I'm going to get at that, I'm going to just draw the envelope, like the outside part of the wave. Like right now, the envelope is the whole, that's the envelope of these two waves. But let me show you what I mean. So if we have the red wave and the green wave on top of each other, crest to crest, trough to trough, very nearly trough to trough here, but crest to crest here, we're going to get a maximum. So we're going to get a positive maximum here and a negative maximum here. And let's see when, so that's a loud place. Where is it quiet? Right there, where the trough of the green and the crest of the red meet. That's going to cause a kind of a nodal point, a cancellation. Let's keep going. When does it get completely lined up again, where they're in phase and constructively interfering? Right here. So here we're going to have a positive maximum and a negative maximum. When's it going to get out of phase perfectly? Right here. So there we have like a cancellation. And we're back to positive max, negative max at the end. Now when I say I want to draw the envelope, let me show you what I mean. That's the outermost part of the sum of the two waves at any given point. Now what the inside would look like is actually a trigonometric thing. It's kind of like this. But the point is, the sum is loud, quiet, loud, etc. Let's see how well I did compared to the book's drawing. Oh, well, I did a pretty good job. This is what the book did, right? And they're calling the time, because the x-axis in this case is time, they're calling the time between maximum and then next subsequent maximum the beat period. That is to say, the time between two beats. So let's maybe hear what this sounds like. We could talk about it all day long, but what does it sound like? To give you a feeling of what this sounds like, I've brought back my two tuning forks. You may recall these tuning forks are matched, they're the same frequency. If you have the same frequency, you don't get beats. You don't get a place where they are sometimes overlapping constructively and then sometimes destructively. You just get the sound of two forks that are the same frequency. If I put on these little clamps, you recall that that adds a little mass to the fork. It doesn't vibrate quite so fast, and you will have two different frequencies. Let's listen. So those are close. They're not the same. Maybe they're 10 hertz apart, 12 hertz apart, I don't know. But go ahead and listen to what you get when we have them both struck at the same time and sound waves are moving toward you with different frequencies. You can hear the fluttering. Now the time between each flutter is the beat period, how long between the overlapping constructive points. It turns out that there's a formula, and we're going to talk about that in a minute, but let's talk a little bit about beats in a non-sound way. Imagine you're running on the Hillsdale track, right? Let's say you, the person that has a blue head, let's say you're faster than the person you're running with. That means every once in a while, you're going to lap them. You're going to make an entire lap and catch them. Then you're going to pass them and do an entire lap and catch them. At the moment you're side by side, that's like constructive interference. That's like lined up crest to crest. When you guys are in opposite places on the track, like you have gone half a lap, you're perfectly out of phase with that person. That's like the destructive interference. Now think about it. If you two run almost the same speed, is it going to take you a long time to lap them or a short time? You're almost the same speed. It's going to take you a long time to lap them because you get ahead, but you don't get ahead quickly. Eventually you're on the other side of the track from them. And then eventually you catch them. And you're lined up next to each other. But the closer you are to these being the same speed, the longer it takes for the overlapping to occur, the constructive interference when you're side by side. So when we heard the beats of the tuning forks, and these are relatively different frequencies. So the beat frequency is really, really high. Because they're pretty different. Just like the lapping example, if you ran twice as fast as the person, well, you'd lap them a lot. In fact, you'd lap them every 2 laps if you ran twice as fast as they did. But let's make these frequencies closer. Listen again. Now Now the lower I put the clamps on this one, the closer they get to be in frequency. It's like you running with someone who's almost the same speed as you. Listen to these now. Pretty close, not really close, but pretty close, closer. I don't know if you can tell, but the beats aren't coming as often. They aren't as frequent, the beats. The time has gotten greater between each beat. Let me lower this still. Now listen to how close these are now. Now I can make them closer still. And you may be getting tired of this, so I will do it this last time. But now that they're even closer, they're almost the same note, only a couple hertz apart. Now there's only a couple beats per second. That's pretty cool. You've probably seen a visual beat when you were in a car. You're sitting at a left turn situation at a traffic light. You got your turn signal on. You see the flasher on your dashboard indicating that your left turn signal is on. And then you kind of look over the steering wheel to the car in front of you who's got their turn signal on, but they're driving a Prius and you're driving a Honda, whatever. Sometimes you'll notice that your lights flash at the same time, and then they get out of phase, and then they get back in phase, and then they get out of phase, and then they get back in phase. That's kind of a visual beat. The last thing I'd like to talk about before I do the formula is I'd like to show you where beats actually happen in real life. This phenomenon of beats is actually how musicians tune an instrument. If you're in an orchestra, let's say, the first violinist, the concert mistress or concert master, comes out and he or she plays a note. Let's say they play the note A. Everyone else in the violin section plays that same A on their violin, and they listen for beats between the sound being produced by the concert master and their instrument. If they're in tune, there will be no beats. But if they're off by a half of a hertz or just a hair sharp or flat, they'll hear beats between their instrument and the one being played by the lead, the concert master. And so you then tune your instrument until the beats go away. Another last thing I'd like to talk about relating to beats are train whistles. This is a toy train whistle, but you're accustomed to hearing this sound, I think. The train whistle, even on real trains, it's important that people not get hit by a train. So we want a whistle that gets everyone's attention. And beats are just sort of aharmonic in a way. Like, this doesn't make, our brains kind of hear that sound and we pay attention to it. Because there are beats there and we're not accustomed to hearing beats. If you didn't hear the beats, well, check out what the train whistle really is. I'm going to cover, it has 4 holes. It's 4 different notes being sounded at the same time. Let me cover 3 of them you will hear. Now I'm going to cover 3 different ones. But when sounded all together, it has a kind of a throbbing, throttling sound. This old thing is an antique train whistle that was made for kids who had model trains in their playrooms or their rooms, 50, 60 years ago, before we had electric horns and stuff. It's kind of neat. I picked it up at a secondhand store, but it's got 3 different whistles, and if I cover 2 of the notes, you'll hear that. Cover the 2 outside ones. left ones. But played all together, kind of neat. It only lasts for a second, so it's hard to hear, but you can hear this kind of throbbing. So that's beats. The last thing is just looking at, there's a formula. And it turns out that the beat frequency, the number of beats you hear, the frequency of the beat, is simply the difference between the two frequencies. Now, because I wrote it as F2 minus F1, generally speaking, when you employ this formula, you put the larger frequency first so that when you subtract the smaller frequency, you get a positive number. But the formula would work either way. You would just get a negative answer, and you would use the absolute value of the difference. Okay? So, for example, a moment ago when we had the two forks, and they were, I heard about 2 beats per second. They must have been about 2 hertz different. And we know one of them is 440, and we know one of them is 440 hertz. And by putting the black clamps, let's say we lowered the other one to 438, the difference between those two frequencies is the beat frequency. So in this case, 440 minus 438 is 2. And that's how many beats we heard per second. 2 beats. Wah, 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 wah. So that's it. That's beats. Beats are kind of cool. Yeah, I hope you enjoyed that. We'll see you next time.